We can build a network, train it, and stop it from overfitting, but there's a quieter problem we've ignored. Deep networks are genuinely hard to get training at all. The signal flowing through them can quietly explode or fade to nothing. Today, the two unsung tricks that keep that signal alive: good initialization and normalization. This is what makes deep actually trainable. Picture a number flowing through a deep network. At each layer, it gets multiplied by weights and summed. If those weights are a bit too large, the signal grows layer after layer until it explodes into enormous values. A bit too small and it shrinks, halving and halving until it vanishes to nearly zero. Either way, by the time it reaches the end or the gradient flows back, there's nothing useful left. It starts before training even begins, with how we pick the initial weights, set them all to zero, and every neuron learns the same thing: useless. Pick them randomly but too large, and the signal blows up; too small, and it dies out. The very first numbers you choose decide whether the network has a chance. So we don't guess, we choose them carefully. The fix is smart initialization. Methods like Xavier and He scale the random weights based on how many inputs each neuron has. The idea is simple: keep the size of the signal roughly constant as it passes through each layer, not growing, not shrinking. He initialization is tuned for real networks specifically. It's a one-line change, and it's the difference between a deep network that trains and one that just sits there, dead. Good initialization gets you started, but there's a second problem during training. As the weights in early layers update, the distribution of values feeding into later layers keeps shifting underneath them. Every layer is chasing a moving target. This constant drift makes training slow and twitchy. We'd love to pin those distributions down. That's what batch normalization does. Inside the network, it takes each layer's outputs across the current mini batch and recenters them, subtract the mean, divide by the standard deviation. Now every layer receives inputs with a stable shape, roughly mean 0, variance 1. No matter how the earlier layers shift, the moving target stops moving. But forcing everything to mean 0 and variance 1 is too rigid. Sometimes a layer needs a different range. So batch norm adds two learnable knobs: a scale, gamma, and a shift, beta. After normalizing, the network can stretch and move the distribution to whatever it actually wants. It gets stability by default, but keeps the freedom to undo it if needed. The payoff is big. Networks with batch norm train dramatically faster. You can use higher learning rates without diverging. They're less sensitive to how you initialized. And because each batch's statistics are slightly different, it even adds a little noise, a mild regularization bonus on top. For years, batch norm was the trick that made very deep networks practical. But batch norm has an Achilles heel. It depends on the batch. Its mean and variance are computed across the examples in a mini batch. So if your batch is tiny, those statistics are noisy and unreliable. And for sequences like text, where examples vary in length and you often process one at a time, batch statistics barely make sense. We needed normalization that doesn't depend on the batch at all. Enter layer normalization. Instead of normalizing each feature across the batch, it normalizes across all the features within a single example. Each input is standardized on its own, completely independent of its neighbors. No batch needed. That independence is exactly what sequences and transformers want, which is why layer norm, not batch norm, lives inside every large language model. The newest models go one step simpler with RMS norm. It drops the mean subtraction step entirely and just rescales by the root mean square of the values. Fewer operations, almost the same benefit, and a little faster. It's the normalization quietly running inside many of today's frontier language models. So the map is clean. In convolutional networks for images, where batches are large and uniform, batch normalization rules. In transformers and anything sequential, layer normalization, or its linear cousin RMS norm, is the standard. Same core idea everywhere, keep the activations in a sane, stable range so the signal never explodes or dies. And that completes the picture. Good initialization gives the signal a fair start. Normalization keeps it healthy all the way through. Together, they're why we can train networks hundreds of layers deep instead of just a handful. That's also the end of our foundations. The neuron activations, loss, gradient descent, backprop, optimizes, regularization, and now normalization. You now understand how a neural network actually learns end to end. Next, we go under the hood into the math that powers all of it, vectors, matrices, and the language of deep learning. See you in the next one.